Hello and welcome to SLURM Basics. In this video, we'll cover some core concepts surrounding scheduling your job, a few useful commands for monitoring and modifying your job on MSU's High Performance Computing Center, and lastly, a few key job scheduling policies. So let's get started. The first question we want to answer is, what is a scheduler? To answer this question, let's take a quick look at the layout of HPCC. HPCC maintains several clusters. Each is named by the processor or coprocessor type and the year the cluster was installed. So for example, you'll see names like Intel 14, Intel 16, and this year AMD 20. Each cluster consists of a group of compute nodes with very similar hardware. Typically, all nodes have specific processors, but there's some variation in the configuration. So some nodes might have different coprocessors, a different size of memory, or a different number of CPUs. Development nodes are representative nodes of each of the clusters on HPCC. To run your work on more than just one of these single nodes, you have to go through the scheduler. On HPCC, SLURM is the job scheduler that we use to provide users access to the compute nodes. This is how users access the batch system to queue up jobs, and also how you'd access compute nodes directly through interactive sessions. So in the next few minutes, we want to take a look at a few key SLURM concepts. The first concepts are those of accounts and partitions. So an account is an access group that gives you privileges to different resources on the cluster. All nodes on HPCC can be classified as either a Buyin or a non-Buyin node. Nodes that have been purchased by faculty are called Buyin nodes, and nodes that are not owned by a specific user are called non-Buyin nodes. All account holders have access to HPCC resources subject to several job restrictions, but if your PI or your collaborator owns nodes in the cluster via the Buyin program, your access group will be the group name specified at the time the nodes were purchased. If you don't own nodes in the cluster, your default account will be general. To find your default account, use the HPCC power tool buyin_status with a -L option. So let's take a look at my access group here. So here I am, I'm already logged into the HPCC, and I'm using a test account here called class 11. And so if I take a look at the modules loaded, I can see that I don't have power tools loaded, therefore I can't use the buyin_status command. So I need to first load power tools. Now that I have power tools loaded, I can check my account status. So here you can see that the accounts that I only have access to a single account called class res, and my default account here is obviously class res. And so I am a member of a Buyin group. However, if I pan to my personal account here and I take a look, you can see I have power tools loaded, and I check my status. You can see that I don't belong to any Buyin groups, and therefore my default account status is general. The next concept we want to address is that of a partition. A partition is a logical unit that spans all clusters on HPCC and breaks up the compute resources into usable units based on node specification. The setup of partitions varies across computing environments, and on HPCC, we have 3 main partitions. If you're in a user group that has access to Buyin nodes, then you'll automatically have access to your own Buyin partition. This partition consists of all nodes purchased by your faculty that you're affiliated with, plus all non-Buyin nodes. Buyin partitions have the highest scheduling priority. Note, this priority only applies to the nodes that are purchased. If your job requires more resources than those that are purchased, then You'll have access to non-Buyin nodes, but you'll have equal consideration as a general account user. Now, if you don't have a Buyin group or your job requires more resources than is available on your own nodes, your job can utilize any of the following partitions. The second partition is the general long partition, and it includes all non-Buyin nodes. Jobs that request a wall time greater than 4 hours are automatically submitted to this partition. A subset of this partition is the general long big mem partition, and this includes nodes with memory size greater than or equal to 256 GB or 40 or more CPUs. Jobs requesting high memory or core count are automatically submitted to this partition. This ensures that large jobs get priority to large nodes over jobs that can run elsewhere in the cluster. Similarly, the general long GPU partition consists of nodes with coprocessors. Jobs that request GPUs are automatically submitted to this partition. Lastly, all nodes in the cluster are made available via the general short partition. Jobs that request a wall time of less than or equal to 4 hours are automatically submitted to this partition. This partition has the lowest priority. So to prevent jobs submitted to this general short partition from being continually bumped, these jobs are also submitted to the general long partition. So let's take a quick look at how accounts and partitions are used on HPCC. In most cases, you will not need to specify a partition when submitting a job on HPCC. Your default account will determine how your job gets submitted, and SLURM's Job Submit plugin will assemble a partition list automatically for you. So users only need to specify resource requirements. For example, if your default account is a Buyin account, so for example, if I were submitting using my class 11 account and I have access to the Buyin partition class res, and my job would be submitted to the following partitions. If my job requested less than or equal to 4 hours of wall time, then it would automatically get submitted to a general long partition or sub-partition, so either general long big mem or general long GPU, and a general short partition. If I'm requesting a job with high core count or high memory usage, then it would be the general long big mem partition. Similarly, if my job requested GPUs, I would instead have access to the general long GPU partition. In addition, my job would also be submitted to my own Buyin partition, in this case, the class res partition. If my job were requesting more than 4 hours of wall time, then I would not have access to the general short partition. Similarly, if my default account status is general, the only difference here would be that I don't have access to a high priority partition. Now notice that this example is based on a default account. But what if I want to use an account that is not my default account? So this is the case in which I have access to multiple accounts. During job submission, you can specify the account to be used on the command line using the -A option followed by the account name you would like to use. Or you can also specify it in your batch script using the directive sbash-a followed by your account name. Generally, from this example, we can see that jobs with a wall time of less than or equal to 4 hours are able to run on the largest set of nodes, but jobs with large resource requests have higher priority for those resources over smaller jobs, because these jobs are more difficult to schedule. Several factors affect the job's priority. The first is the job's age. This is the time from when the job is submitted until the resources become available. The maximum value this factor can take is 60,000 after 30 days of waiting for resources. The next factor is fair share. This factor decreases a user's priority based on their recent usage. So the higher your recent usage, the lower your priority will be. The maximum value your fair share can be is 60,000 for no recent cluster usage. The next factor affecting your priority is the size of your job. For every CPU you request, 100 points are added to your priority, and for every gigabyte of RAM you request, 20 points are added to your priority. Notice the maximum value that can be contributed to your priority due to the CPU reservation is 52,000, and this is based on the 520 core limit. The last factor is the quality of service. This factor ensures that buy-in jobs are always above the backfill scheduler's minimum priority for reserving resources. If you want to check the priority of any jobs you have pending in the queue, use the sprio command followed by the -u option and your user ID. For more about job priority, follow the link in the comments below. In this next section, we'll take a quick look at a few useful commands for monitoring your job on HPCC. So let's take a quick look at a few commands that are useful for monitoring the state of our jobs in the queue. The first command is sq. And this command typically shows all the jobs that are running the queue. As you can see, there's a lot of output there. So let's use sq followed by, and pipe that into more. All right, so what you can see here are the job IDs, the partition to which those jobs have been submitted, and the job name if one has been provided. You can also see the user who's running that job and the current status of the job. PD here indicates that the job is pending in the queue. If it were running, it would have an R, and if the job is just exiting the queue, then it'll have the CG for canceling job. And then you can see also the time for which a job is in the queue, if it's currently running, and the number of nodes it's been running on. Once these jobs get assigned, you can see a list of the nodes on which they are running. Right now, what you can see is the reason these jobs are currently pending in the queue. So for instance, this job here is currently pending in the queue because the resources are not available. Now, since I don't have any jobs running in the queue, I'm going to use the user LEESEOKJ. Okay, so if I wanted to see all the jobs that this user has in the queue, I would use SQ followed by -u and the username. And here I can see very quickly all the jobs that this user has either pending, canceling, or running in the queue. And so this is really useful. If I instead wanted to see all the jobs that were being run by my group, then I could use the -- account flag. So I'd say SQ -- account, and let's say I want to look at all the class res jobs in the queue. So let's pick another account to look at. So let's say we wanted to look at, there's a PTG group on here. So we want to look at all the jobs being run by that group. I can see very quickly that there are a lot of jobs being run by this group. And I can see similarly what the status of those jobs are, and if they are running, what nodes they're running on, if they're waiting, why they are waiting, and so on and so forth. So one key thing to note here is that the partition name here is PTG because these jobs are running on the PTG buy-in partition. If instead I wanted to look, say, at all jobs that are running on the general long big mem partition, I can use here and replace account with -- partition equal general long big mem. And here I can see all jobs that are running on the general long big mem partition and their current status. So this is really useful for giving me all kinds of cool information. The other thing that may be of interest to me is the status of a partition. So for instance, if I want to determine how quickly my job is likely to run, I can look at the partition to which it will be submitted and see what's the status of those nodes. And the command for that is sinfo -s. And here I can see the status of each partition. I can see If the partition is available, I can see the wall time limit for each partition. And then I can also see how many nodes are available within that partition, how many are idle, how many are offline, and the total number of nodes that are a part of that partition. I can also have access here to a node list, and you can see from this brief view here that the general short partition is the biggest partition because it includes all nodes in the cluster. So some other things that might be useful that I'm not able to see from this view is the information about a specific partition. So let's suppose that I'm interested in the general long big mem partition. Then I can use the same command sinfo followed by -p, general long big mem, -r-l, and here I can see very quickly a summary of the number of drained nodes, and I can see which nodes are actually drained, and the number that are in the mixed state. This means some CPUs are idle on those nodes and some are being utilized, and the nodes that are fully allocated. So this helps me to see that within the general long big mem partition, there are potentially 9 nodes that I could schedule jobs to run on right now. What I don't know is any of the attributes of those nodes. To look at the attributes of those nodes, I want to use the same command sinfo followed by -n, uppercase N, -l, -r, and -p. And so let's see what we got there. So here, once again, I can see the name of each node. I can see the partition it's in. I can see the state. I can see the number of CPUs that that node has. And I can see how many sockets and cores per socket are available. I can see the size of the RAM, and this is given in gigabytes. And I can also see the size of temp disk. Additionally, I can see a feature list. So if I wanted to use directTest to access nodes with a particular feature, I could do that. I could see the reason why a node is drained or offline as well. So this is all really useful. The other command that I can use to show me more particular information about one of these nodes, so let's suppose I wanted to take a look at LAC 252, I can use scontrol show node. -a followed by the node name. So here this node has 14 cores per socket, 20 are allocated, and so I can tell that about 8 cores are available here. I can see a feature list, and then I can see whether there are GPUs associated with this node, which there aren't. Other things I can see is the partitions in which this node is available. I can also see the memory that is available and what's been allocated and what's free. I can see that this node has 2 sockets and 1 board and a whole bunch of other really useful statistics. Lastly, if I just want to look at all nodes that are active, I don't want to see those that are offline or drained, I can use the power tool command active_nodes. And I'll get a full list here, so I'm going to pipe that into the more command of all nodes that are online. So here I can see this information a little bit more cleanly for each node. I can see the number of CPUs that are available, the CPU load, the total memory, how much of that memory is free, and whether the node has been allocated. And I can also see a feature list. And I can also see whether it is a Buyin node or a non-Buyin node. Typically, a little over 50% of the cluster consists of owner nodes. So this is really useful for determining how likely my job will run if I submit it right away. So let's look at a few other really useful SLURM commands. So if you want to launch a job on HPCC, the command srun is used for launching that job interactively on the command line, and we'll talk about that more in the interactive job submission tutorial. If you want to launch a job from batch script, sbatch is the SLURM command for doing this. And so let's go back to the R example. And so I'm going to cd to the R tutorial example here. So let's take a look at this R tutorial directory, and here you can see that I have an SBAT script here that submits the submit_k-means analysis script. So I can use the SBAT command to launch that job. And then you can see my job submission number there. So if I use SQ-U followed by my username, so $user, I can see that my job is currently pending in the queue and it's been submitted to the general long partition. This is really useful. If I use QS-U followed by my username, I get no output. And again, if I use SQ-U followed by user, I also get no output. This is because my job has already exited the queue. Then if I take a look here, I can see that I have output from this job number. If I use scontrol, show job, followed by the job ID, grab that job ID, I can see some really useful information regarding my job runtime, submit time, and eligible time. I can also see the actual start and end time of my job, and I can see that this job took seconds to run. The other things that I can tell here are the partition the job ran in, whether the job completed, and also to where the job was submitted from, and where the standard output and error messages have been sent. I can see also the command I used to submit the job. So pretty useful information. I can view the node the job ran on and the resources that I requested. So the other thing I can do, if at some point I realize that something about my job script isn't quite right, but I've already submitted this job, I can cancel the job. So let's try submitting this job again to the queue. Let's submit the job again. And then we can see that the job's submitted and SQ, and let's cancel this job, followed by the job ID. And if I do SQ, followed by my username, I can see that I no longer have a job in the queue. If I ls to look at my directory here, I can see that I don't have any output from this job here, and that's because the job was canceled. If I scontrol, show job, followed by that job ID, I can also see that in the job state that job was canceled. The other thing I can do instead of canceling a job is I can modify the job. And to do that, you first want to place a hold on the job, and then you want to update that job with any new resources or information that you need to provide. And finally, you want to release the job again so that it runs. So let's look at a quick example here. If I take a look at that directory, you can see that I've got this submission script, submit k-means _n PDF, and let's use the sbatch command to submit this job to the queue. So there my job is in the queue. I type SQ and I can see the status of my job. I can see that it's pending because it's waiting to accrue priority. If I want to hold this job so I can modify the resource request, I can type scontrol hold followed by the job number, and there I type QS again. I can see that my job's still pending, but now the reason it is pending is because it's being held by the user. From this QS view, I can also see more details about my job request. I can see that I've requested 1 node and 28 CPUs, and the memory I've also requested 250 megabytes. So here I know that this job should be a single core job, and so I want to update the number of CPUs requested to be 1. So if I take a look here at the job details using S-Control show job followed by the job ID, I can see a number of variables here, but the one I'm interested in is this one, which shows the number of CPUs that this job has requested. So this variable here, num CPUs, is the one I want to update to 1. So here we are. So to update this variable, I type S-Control update job, followed by the job number, and num CPUs equal 1. If I take a quick look here using SQ, I can see now that the number of CPUs requested has been updated to be 1. I can also see that my job is still pending in the queue. Now, all that's left for me to do is to release this job so that it can be run. And to do that, we type S-Control release followed by the job ID. And if I type QS again, I can see now my job is in the queue, it's pending, but instead of being held by the user, it's just waiting to accrue priority. So once the resources become available, this job should then run. So just to review the commands we covered today, sbatch for submitting a job script to the queue, scancel to cancel a job while it is running, scontrol displays the SLURM state of that job, and sinfo displays the state of the partitions and the nodes within those partitions. Sq shows us the state of running jobs on the cluster, and alloc for job execution, or to initiate a job in real time. In other words, to start an interactive job. We also covered srun, which is for launching a job interactively. So a couple other things you need to know about running your job on HPC. There is a CPU time limit for general accounts. Buyin accounts have unlimited access, but general accounts are limited to 1 million CPU hours per calendar year. Queue limits apply to general accounts, once again, but not to Buyin accounts. So you can schedule your job to run at most 7 days or 168 hours, and you can utilize at any one time 520 cores. You can queue up to 1,000 jobs and have those jobs waiting in the queue. So I hope this was useful for you in terms of getting started with SLURM. If you have questions going forward, feel free to reach out to anyone on our team at contact@icer.msu.edu. Thanks for joining us.